Before we begin, let me ask you something gently. Where are you listening from right now? And what time is it there for you? You don't need to answer out loud. Just notice it for a moment. A place, a time, a quiet setting somewhere in the world where this moment is happening. That awareness alone can help the mind settle into listening rather than striving. Now let's begin calmly, without rushing. The nervous system is not something most people think about day to day. It works quietly in the background, managing countless processes without asking for attention. Yet it is one of the most complex and influential systems in the human body. Every sensation you feel, every movement you make, every reaction you have to the world is shaped in some way by the nervous system. At its most basic level, the nervous system is the body's communication network. It allows different parts of the body to send messages to each other quickly and precisely. These messages travel as electrical and chemical signals, moving along specialized cells called neurons. Some of these signals move incredibly fast, reaching speeds of over 100 meters per second, allowing the body to respond almost instantly to changes in the environment. The nervous system is traditionally divided into two main parts. The central nervous system consists of the brain and the spinal cord. This is the processing center, where information is received, interpreted, and decisions are made. The peripheral nervous system includes all the nerves that branch out from the brain and spinal cord, reaching the skin, muscles, organs, and glands. These nerves carry information back and forth, connecting the central nervous system to the rest of the body. Within these broad divisions, the nervous system becomes even more specialized. Some nerves carry sensory information. They tell the brain what is happening in the body and in the environment: temperature, pressure, pain, position, movement, sound, light. Other nerves carry motor instructions, telling muscles when to contract and relax. Still others regulate internal processes like digestion, heart rate, breathing, and blood vessel tone. Much of this activity happens without conscious awareness. You do not have to think about telling your heart to beat or your lungs to breathe. The nervous system manages these functions automatically, adjusting them moment by moment to meet the body's needs. One of the most important features of the nervous system is its adaptability. It is not a fixed system. It changes constantly in response to experience, learning, injury, and aging. This ability to change is known as neuroplasticity. For many years, scientists believed that the adult nervous system was largely unchangeable, but research has shown that it continues to adapt throughout life. This adaptability allows people to learn new skills, form new memories, and recover at least partially from injuries. It also means that habits, patterns of thought, and repeated behaviors can shape how the nervous system functions over time. The nervous system also plays a central role in how the body maintains balance, a state known as homeostasis. Homeostasis refers to the body's ability to keep internal conditions stable despite changes in the external environment. Temperature, blood pressure, oxygen levels, and blood sugar are all regulated in part by nervous system activity. When the nervous system detects a deviation from the optimal range, it helps initiate corrective responses. If body temperature rises, mechanisms that promote cooling are activated. If blood pressure drops, responses that increase it are triggered. These adjustments usually happen smoothly and without conscious effort. Another essential role of the nervous system is coordination. Movement, for example, is not simply a matter of muscles contracting. It requires precise timing and communication between multiple muscle groups, sensory feedback from joints and skin, and constant adjustment based on position and balance. The nervous system integrates all of this information to produce smooth, coordinated action. Even simple movements, like standing up from a chair, involve complex neural processes. The brain anticipates the movement, sends signals to the appropriate muscles, receives feedback about balance and position, and makes rapid adjustments to maintain stability. As people age, some aspects of nervous system function change. Reaction times may slow slightly. Sensory perception may become less sharp. Reflexes may be less brisk. These changes are part of normal aging and do not necessarily indicate disease. Importantly, the nervous system often compensates by relying more on experience, pattern recognition, and predictive control. For example, older adults may move more deliberately, using visual cues and learned strategies to maintain balance. This reflects adaptation rather than decline. The nervous system is adjusting how it processes information to maintain function. Another key fact about the nervous system is that it operates both consciously and unconsciously. Conscious activities include deliberate movement, focused attention, and intentional thought. Unconscious activities include reflexes, automatic regulation of organs, and many emotional responses. Emotions themselves are closely linked to nervous system activity. They are not just abstract experiences, but involve coordinated changes in brain activity, nerve signaling, hormone release, and body sensations. This is why emotions can feel physical: a tight chest, a warm face, a sinking feeling in the stomach. Memory is also deeply tied to nervous system function. Different types of memory are processed and stored in different neural networks. Short-term memory, long-term memory, procedural memory, and emotional memory each rely on distinct but interconnected parts of the brain. The nervous system does not store memories like files in a cabinet. Instead, memories are patterns of neural connections that become stronger with repetition and emotional significance. This is why frequently recalled information becomes easier to remember, and why emotionally charged experiences are often remembered more vividly. Another important fact is that the nervous system is highly energy dependent. Although the brain accounts for only a small percentage of body weight, it consumes a significant portion of the body's energy. This energy supports continuous electrical signaling, chemical transmission, and cellular maintenance. Because of this high energy demand, the nervous system is sensitive to factors such as oxygen supply, blood flow, blood sugar levels, and overall metabolic health. Disruptions in these areas can affect concentration, mood, and physical coordination. The nervous system is also deeply interconnected with other systems in the body. It works closely with the endocrine system, which releases hormones, and the immune system, which defends against infection and injury. Communication between these systems allows the body to respond in a coordinated way to stress, illness, and recovery. For instance, during illness or injury, nervous system signals can influence immune responses, while immune signals can affect how the nervous system functions. This bidirectional communication helps explain why physical illness can affect mood and cognition, and why psychological stress can influence physical health. One of the most remarkable aspects of the nervous system is its redundancy. Many functions are supported by multiple pathways. This means that if one pathway is damaged, others can sometimes compensate. This redundancy contributes to resilience and partial recovery after injury. At the same time, some neural structures are highly specialized and vulnerable. Damage to specific areas of the brain or spinal cord can result in precise and predictable deficits, reflecting the organized layout of neural functions. As we move forward, we'll explore these structures and processes in more depth. We'll look at how different parts of the nervous system specialize, how signals are transmitted, how regulation occurs automatically, and how the system adapts across the lifespan. For now, There is nothing you need to memorize or hold on to. This is not a test. It's simply a calm exploration of how one of the body's most important systems works, layer by layer, at a steady and unhurried pace. As we continue, there's no need to recall everything that's already been said. The nervous system itself doesn't work by holding everything at once. It works through flow, through signals moving where they're needed, when they're needed. You can listen in the same way, letting information pass through without effort. At the center of nervous system function is the neuron. Neurons are specialized cells designed to transmit information. Unlike most other cells in the body, neurons are shaped in a way that supports communication over distance. A typical neuron has three main parts: a cell body, branching extensions called dendrites, and a long fiber known as the axon. The dendrites receive incoming signals from other neurons. The cell body processes these signals. If the combined input reaches a certain threshold, the neuron generates an electrical impulse that travels down the axon. This impulse is called an action potential. It is an all-or-nothing event, meaning it either occurs fully or not at all. Action potentials travel along the axon by a process involving changes in electrical charge across the neuron's membrane. This movement depends on ions, charged particles such as sodium and potassium, moving in and out of the cell through specialized channels. These channels open and close in precise sequences, allowing the electrical signal to propagate rapidly. One remarkable fact is that the speed of signal transmission varies. Some axons are wrapped in a fatty, insulating substance called myelin. Myelin allows electrical impulses to travel much faster by enabling the signal to jump between gaps in the insulation, a process known as saltatory conduction. This increases efficiency and reduces energy consumption. Not all axons are myelinated. The nervous system uses different speeds depending on function. Reflexes and precise movements often rely on fast conducting fibers. Other signals, such as those involved in pain or internal regulation, may travel more slowly. When an action potential reaches the end of an axon, it does not jump directly to the next neuron. Instead, it arrives at a junction called a synapse. The synapse is a tiny gap between neurons, and communication across this gap is chemical rather than electrical. At the synapse, the electrical signal triggers the release of chemical messengers known as neurotransmitters. These molecules cross the synaptic gap and bind to receptors on the receiving neuron. Depending on the type of neurotransmitter and receptor involved, this binding can either excite or inhibit the next neuron. This balance between excitation and inhibition is critical. The nervous system is not simply about turning things on. It is equally about preventing excessive activity. Inhibition allows for precision, stability, and control. Without it, neural activity would become chaotic. Different neurotransmitters serve different roles. Glutamate is the primary excitatory neurotransmitter in the brain involved in learning and memory. Gamma-aminobutyric acid, often called GABA, is the primary inhibitory neurotransmitter, helping regulate neural activity and prevent overstimulation. Other neurotransmitters include acetylcholine, which plays a key role in muscle movement and attention; dopamine, involved in motivation, reward, and movement regulation; serotonin, which influences mood, appetite, and sleep-wake cycles; and norepinephrine, which affects alertness and stress responses. These chemical systems interact in complex ways. No single neurotransmitter works in isolation. The balance between them shapes perception, movement, mood, and cognition. Changes in these systems can influence how a person feels and functions. Another important fact about neural communication is that it is not linear. A single neuron can receive input from thousands of other neurons. Likewise, one neuron can influence many others. This creates vast networks rather than simple chains. These networks allow for integration. Sensory information, for example, does not travel along a single path. It is processed, compared, filtered, and interpreted across multiple brain regions. This distributed processing allows for flexibility and robustness. Timing is also essential. The nervous system relies not only on which neurons fire, but on when they fire. Precise timing patterns allow the brain to distinguish between different types of information and coordinate complex actions. For example, coordinated movement requires muscles to activate in specific sequences with precise timing. A delay of even a fraction of a second can disrupt balance or accuracy. The nervous system continuously adjusts timing based on sensory feedback. Another key feature of neural communication is plasticity at the synapse. Synapses are not fixed connections. Their strength can change depending on how often they are used. When two neurons frequently communicate, the synapse between them can become stronger, making future communication more efficient. This process underlies learning and memory. Skills improve with practice because the neural circuits involved become more efficient. Memories persist because the synaptic connections representing them are reinforced. Conversely, connections that are rarely used may weaken over time. This pruning helps the nervous system remain efficient, focusing resources on relevant pathways. Plasticity continues throughout life. While it may occur more slowly with age, it does not stop. This means that learning, adaptation, and recovery remain possible well into older adulthood. The nervous system also includes specialized support cells known as glial cells. For many years, glial cells were thought to play only a passive role, providing structural support. Research has shown that they are actively involved in neural function. Glial cells help maintain the chemical environment around neurons, support myelin formation, provide nutrients, and participate in immune defense within the nervous system. Some glial cells even influence synaptic activity and communication. This highlights an important fact. Neurons do not work alone. Nervous system function depends on a complex ecosystem of cells working together. Another aspect of nervous system communication is feedback. Many neural pathways include loops that allow output to influence future input. This feedback enables regulation and fine-tuning. For example, when you move your arm, sensory receptors in muscles and joints send feedback to the brain about position and tension. This information allows the brain to adjust the movement in real time. Feedback also plays a role in emotional regulation, learning, and decision-making. The nervous system constantly monitors the outcomes of its actions and adjusts accordingly. The spinal cord deserves special attention here. It is not just a conduit between the brain and the body. It also processes information independently. Many reflexes are mediated at the spinal level without direct involvement of the brain. This allows for rapid responses to potential harm. If you touch something hot, the spinal cord can initiate withdrawal before the brain has fully processed the sensation. This speed is protective. At the same time, the brain can modulate spinal reflexes, increasing or decreasing their sensitivity based on context. This illustrates the layered organization of the nervous system, with multiple levels of control. Another important fact is that the nervous system is asymmetrical in some functions. While the left and right sides of the brain are largely similar, certain functions tend to be more dominant on one side. Language, for example, is often more left lateralized, while spatial processing may be more right lateralized. However, this lateralization is not absolute. Many functions involve both sides working together. The two hemispheres are connected by a large bundle of fibers called the corpus callosum, which allows information to be shared. Disruptions to this communication can affect coordination and integration of function, highlighting the importance of connectivity. As people age, changes in neural communication can occur. Signal transmission may become slightly slower. Synaptic efficiency may change. Myelin integrity may decline in some regions. These changes are gradual and variable. Importantly, the nervous system often compensates by recruiting alternative pathways, relying more on experience and predictive processing. This adaptability helps maintain function, even as underlying mechanisms change. Understanding these facts can help reframe how we think about the nervous system. It is not a static machine that either works or fails. It is a dynamic, adaptive system that responds continuously to internal and external conditions. As the explanation continues, you may notice that some details naturally stand out, while others fade into the background. That's exactly how the nervous system itself works. It prioritizes, filters, and focuses without needing conscious instruction. You can allow your attention to do the same. One of the most important organizational principles of the nervous system is how it separates voluntary and involuntary functions. This separation allows the body to manage both deliberate actions and automatic processes efficiently, without confusion or overload. The somatic nervous system is responsible for voluntary movement and conscious sensory perception. When you decide to move your arm, speak, or turn your head, the somatic system is involved. It also carries sensory information from the skin, muscles, and joints to the brain, allowing you to perceive touch, temperature, pain, and body position. Somatic motor pathways typically involve a direct connection between the central nervous system and skeletal muscles. A single motor neuron extends from the spinal cord or brainstem directly to the muscle it controls. This direct pathway allows for precise and rapid control of movement. In contrast, the autonomic nervous system regulates involuntary processes. These include heart rate, blood pressure, digestion, respiration, pupil size, and glandular secretion. These functions occur without conscious effort, allowing the body to maintain internal stability while attention is directed elsewhere. The autonomic nervous system is further divided into the sympathetic and parasympathetic systems. These two branches work together, often in opposition, to regulate physiological activity. The sympathetic nervous system prepares the body for action. It increases heart rate, redirects blood flow to muscles, dilates airways, and mobilizes energy resources. This system is activated during physical activity, stress, or situations that require heightened alertness. The parasympathetic nervous system supports restoration and maintenance. It slows heart rate, promotes digestion, supports nutrient absorption, and facilitates recovery processes. This system is more active during periods of rest and low demand. Importantly, these systems are not simply on or off. They operate on a continuum, adjusting their influence moment by moment. Most of the time, both systems are active to some degree, with one exerting more influence depending on circumstances. This balance allows for fine-tuned regulation. For example, during light activity, heart rate increases modestly without fully engaging a stress response. During relaxation, heart rate slows without shutting down readiness entirely. Another important division within the autonomic system is the enteric nervous system, often referred to as the second brain. The enteric system consists of extensive neural networks embedded in the walls of the gastrointestinal tract. It can function independently of the brain and spinal cord, regulating digestion, nutrient absorption, and gut motility. The enteric nervous system contains millions of neurons and uses many of the same neurotransmitters found in the brain. While it communicates with the central nervous system, it can operate autonomously, coordinating digestive processes without conscious input. This independence helps explain why digestion can continue during sleep or distraction, and why gastrointestinal function can be sensitive to stress and emotional states. The nervous system also organizes information hierarchically. Higher brain regions, such as the cerebral cortex, are involved in planning, decision-making, and conscious awareness. Lower regions, including the brainstem and spinal cord, manage basic life support functions and reflexes. This hierarchical structure allows higher centers to modulate lower ones. For example, while breathing is automatic, you can voluntarily alter your breathing pattern for speech or intentional breath control. This demonstrates coordination rather than competition between levels. Another key organizational feature is sensory mapping. The brain maintains maps of the body and environment. In the somatosensory cortex, different body parts are represented in specific regions. Areas requiring fine sensory discrimination, such as the hands and face, occupy disproportionately large cortical areas. Similarly, the motor cortex contains maps that control movement. These maps are adaptable. With use and training, representations can expand or shift, reflecting neuroplasticity. This adaptability allows the nervous system to reorganize after injury or in response to changing demands. For example, if one sensory pathway is compromised, others may become more sensitive to compensate. The nervous system also relies on integration across sensory modalities. Vision, hearing, touch, and proprioception do not operate independently. Information from these systems is combined to create a coherent perception of the world. Balance is a good example. Maintaining balance requires input from the inner ear, vision, and proprioceptive sensors in muscles and joints. The nervous system integrates these signals to adjust posture and movement. If one source of input becomes less reliable, such as reduced vision in low light, the nervous system can increase reliance on other inputs. This flexibility supports stability and function across varying conditions. Another important fact is that the nervous system operates continuously, even during rest. Neural activity does not stop when external demands decrease. Instead, patterns of activity shift. Networks involved in internal monitoring, memory consolidation, and maintenance become more active. These internal processes support long-term function and adaptation. They allow the nervous system to update internal models, integrate experiences, and maintain readiness. The nervous system also plays a central role in regulating arousal. Arousal refers to the level of alertness and responsiveness. It ranges from deep unconsciousness to heightened alertness. Arousal is regulated by networks involving the brainstem, thalamus, and cerebral cortex. These networks adjust sensitivity to sensory input, influencing how easily attention is captured. Changes in arousal affect perception, reaction time, and cognitive performance. Too little arousal can impair responsiveness. Too much can overwhelm processing capacity. The nervous system continuously adjusts arousal to match environmental demands. This adjustment is influenced by factors such as time of day, physical activity, emotional state, and overall health. Another key organizational principle is redundancy. Many functions are supported by multiple pathways and overlapping networks. This redundancy enhances resilience. If one pathway is damaged or temporarily impaired, others may partially compensate. Redundancy is especially important for vital functions such as breathing and heart rate regulation. Multiple control centers ensure that these processes continue even if one area is compromised. At the same time, specialization allows for efficiency. Different regions are optimized for specific tasks, balancing redundancy with precision. As the nervous system ages, organizational changes occur. There may be shifts in how different regions communicate. Some connections weaken, while others strengthen. These changes reflect adaptation rather than simple decline. Experience plays a larger role in guiding behavior. Patterns learned over decades influence responses. Predictive processing becomes more prominent, allowing the nervous system to anticipate rather than react. This can lead to more deliberate, efficient behavior, even if raw processing speed decreases slightly. Another important fact is that the nervous system is deeply influenced by the environment. Sensory input, social interaction, physical activity, and cognitive engagement all shape neural function over time. Environments that provide varied, meaningful input support neural health. Conversely, prolonged isolation or lack of stimulation can affect neural networks. However, stimulation does not need to be intense or constant. Gentle, consistent engagement is often sufficient to support nervous system function. As we continue, we'll explore how the nervous system interacts with the body's internal chemistry, how hormones and immune signals influence neural activity, and how these interactions contribute to overall regulation. For now, simply allow the information to settle. Like the nervous system itself, understanding builds gradually through repeated exposure rather than sudden insight. As we move forward, it may help to remember that the nervous system is not designed for perfection. It is designed for balance, adjustment, and survival across changing conditions. Much of what it does involves constant calibration, small, ongoing corrections that keep the body within workable ranges rather than fixed points. One of the central responsibilities of the nervous system is maintaining internal balance over time. This balance is not static. It shifts throughout the day and across the lifespan. The nervous system monitors internal conditions and external demands, adjusting activity to support stability in the face of change. This regulation relies heavily on feedback loops. Sensors throughout the body continually send information about temperature, blood pressure, oxygen levels, chemical composition, and mechanical strain. The nervous system interprets this information and initiates responses that counteract deviations. For example, when blood pressure rises, sensors in blood vessels send signals to the brainstem. In response, the nervous system can reduce heart rate and dilate blood vessels, bringing pressure back down. When blood pressure falls, the opposite adjustments occur. These processes usually happen without conscious awareness. Importantly, regulation does not aim for a single, normal value. Instead, it aims for ranges that shift based on context. During physical activity, heart rate and blood pressure are allowed to rise. During rest, they are allowed to fall. The nervous system continuously adjusts these set points based on circumstances. This flexibility is a strength. It allows the body to respond appropriately to varying demands rather than being locked into rigid patterns. Another key aspect of nervous system regulation involves prediction. The nervous system does not only react to changes after they occur, it also anticipates them. Based on past experience and current context, it generates expectations about what is likely to happen next. This predictive function allows for smoother and more efficient responses. For instance, when you stand up, the nervous system anticipates the need to adjust blood pressure before gravity causes a drop in blood flow to the brain. This anticipation reduces the likelihood of dizziness. Prediction becomes increasingly important with experience. Over time, the nervous system builds internal models of the body and the environment. These models allow it to respond quickly without needing to process every situation from scratch. As people age, predictive processing often becomes more prominent. The nervous system relies more on accumulated experience to guide behavior. This can compensate for slower sensory processing or motor response times. Another important fact is that regulation involves trade-offs. Resources such as energy, attention, and blood flow are limited. The nervous system allocates these resources based on perceived priorities. During physical exertion, resources are directed toward muscles and cardiovascular function. During digestion, blood flow is directed toward the gastrointestinal system. During cognitive tasks, resources are directed toward brain regions involved in attention and memory. These shifts are coordinated by nervous system signaling. They reflect prioritization rather than malfunction. The nervous system also interacts closely with circadian rhythms. These are roughly 24-hour cycles that influence physiology and behavior. The central circadian clock is located in a region of the brain called the suprachiasmatic nucleus, which responds to light signals from the eyes. This clock helps synchronize nervous system activity with the day-night cycle. It influences hormone release, body temperature, alertness, and metabolic processes, while circadian rhythms are influenced by genetics. They are also shaped by environmental cues such as light exposure, activity, and meal timing. With aging, circadian rhythms may shift. Timing of peak alertness and restfulness can change. These shifts reflect changes in nervous system signaling and hormone regulation, rather than dysfunction. Another critical regulatory role of the nervous system involves stress responses. Stress, in this context, refers to any demand that requires adjustment. Stress responses are not inherently harmful. They enable adaptation. When the nervous system detects a challenge, it coordinates a response involving increased alertness, energy mobilization, and focused attention. This response is mediated by interactions between neural circuits and hormonal systems. Problems arise not from the presence of stress responses, but from their persistence or misalignment with actual demands. Regulation involves turning these responses on when needed and off when no longer necessary. The nervous system plays a key role in both activation and recovery. Recovery processes are not passive. They involve active regulation that restores baseline conditions and repairs wear and tear. Another important fact about nervous system regulation is variability. Healthy systems show variability rather than rigid consistency. Heart rate variability, for example, reflects the nervous system's ability to adjust heart rate in response to changing conditions. Greater variability is often associated with better regulatory capacity. Similarly, variability in movement, attention, and emotional response reflects flexibility. Too much rigidity can indicate reduced adaptability. This principle applies across scales. At the cellular level, neural signaling shows variability. At the system level, patterns fluctuate. This variability allows the nervous system to explore different responses and adjust as needed. The nervous system also plays a role in filtering information. At any moment, the sensory environment contains far more information than can be processed consciously. The nervous system filters this input, prioritizing signals that are relevant or novel. This filtering occurs at multiple levels, including the spinal cord, brainstem, thalamus, and cortex. It helps prevent overload and supports focused attention. Changes in filtering can influence perception. For example, during heightened arousal, filtering may be reduced, allowing more sensory input to reach awareness. During fatigue or low arousal, filtering may increase. These shifts reflect adaptive regulation rather than fixed traits. Another important regulatory mechanism is habituation. When a stimulus is repeated without meaningful consequence, the nervous system gradually reduces its response. This allows attention to shift toward more relevant input. Habituation is why background sounds fade from awareness over time, and why repeated, non-threatening sensations become less noticeable. This process conserves resources and reduces unnecessary activation. However, habituation is context-dependent. If a stimulus becomes relevant or threatening, the response can return quickly. The nervous system also supports learning through error correction. When outcomes differ from expectations, neural circuits update their models. This allows future predictions to improve. This error-based learning occurs throughout life. It underlies skill acquisition, behavioral adjustment, and adaptation to change. Importantly, errors are not failures from the nervous system's perspective. They are information. They guide refinement rather than indicating deficiency. As the nervous system ages, the pace of some processes may change. Signal transmission may slow slightly. Sensory thresholds may shift. Integration may require more time. At the same time, accumulated experience often enhances pattern recognition and decision-making. Older nervous systems may rely more on context and prior knowledge to guide responses. This reflects a shift in strategy rather than loss of function. Another key fact is that nervous system regulation is influenced by physical health. Cardiovascular health, metabolic balance, and immune function all interact with neural signaling. Adequate blood flow supports oxygen and nutrient delivery. Stable metabolic conditions support energy availability. Inflammation can influence neural activity, affecting cognition and mood. These interactions highlight the integrated nature of body systems. The nervous system also responds to social and environmental factors. Social interaction, novelty, and meaningful engagement influence neural activity. Isolation and monotony can alter regulatory patterns. However, engagement does not need to be intense or constant. Moderate, consistent interaction is often sufficient to support regulation. One of the most important facts to recognize is that the nervous system is always adapting. Even when changes are subtle or gradual, adaptation is ongoing. This adaptation reflects learning, experience, and environmental influence. It is not a sign of weakness. It is a sign of responsiveness. Understanding regulation helps reframe many experiences. Fluctuations in energy, attention, and responsiveness are often signs of adjustment rather than malfunction. As we move on, we'll explore how these regulatory principles play out across different stages of life, how long-term adaptation shapes function, and how the nervous system responds to cumulative experience over decades. For now, there is no need to summarize or remember every detail. The nervous system itself integrates information gradually. You can allow understanding to form in the same way, slowly, naturally, and without effort. The nervous system begins forming very early in life. In the earliest stages of development, neural cells multiply rapidly and migrate to specific locations. These cells begin forming connections even before birth, laying down the basic architecture of the brain and spinal cord. At birth, the nervous system is already active, but far from complete. Many neural circuits are still immature. This immaturity is not a flaw. It allows for flexibility. Early in life, the nervous system is highly plastic, meaning it can be shaped extensively by experience. During childhood, neural connections are formed at an extraordinary rate. Sensory input, movement, language exposure, and social interaction all influence which connections are strengthened and which are eventually pruned away. Pruning is a normal process in which unused or redundant connections are gradually eliminated, allowing important pathways to become more efficient. This process reflects an important principle. The nervous system develops not only by adding connections, but also by refining them. Efficiency matters. Over time, networks become more specialized and coordinated. As adolescence approaches, development continues, but in a different way. Regions involved in emotional processing and reward sensitivity mature earlier than regions involved in long-term planning and impulse control. This imbalance contributes to characteristic patterns of behavior during adolescence, such as heightened emotional reactivity and increased sensitivity to social input. The nervous system is still undergoing significant reorganization during this period. Myelination increases, improving signal speed and coordination. Long-range connections between brain regions strengthen, supporting more integrated processing. By early adulthood, many neural systems reach a relatively stable configuration. However, stability does not mean rigidity. Learning, skill acquisition, and adaptation continue throughout adulthood. The nervous system remains responsive to experience, though changes may occur more gradually. Throughout adulthood, repeated activities and habits shape neural circuits. Skills that are practiced become more efficient. Frequently used pathways are reinforced. Less used pathways may weaken. This reflects a core principle of nervous system function. Use matters. Neural activity leaves traces. Over time, these traces influence how easily certain patterns are activated. Importantly, this process does not stop with age. While the rate of change may slow, the capacity for adaptation remains. Older adults can still learn new skills, form new memories, and adjust to new circumstances. Research has shown that neuroplasticity persists into later life. While certain types of learning may take longer or require different strategies, the nervous system retains the ability to reorganize in response to experience. Another important aspect of development across the lifespan is compensation. As certain neural processes become less efficient, others may become more engaged. The nervous system often responds to change by recruiting additional regions or alternative pathways. For example, when sensory input becomes less precise, the brain may rely more heavily on contextual information and prior experience. This allows function to be maintained even when raw input quality changes. This compensatory ability reflects intelligence at the system level. The nervous system is not simply reacting to decline. It is actively reorganizing to preserve function. Aging also brings changes in neurotransmitter systems. Levels of certain neurotransmitters may shift, receptor sensitivity may change, and signaling dynamics may alter. These changes can influence mood, motivation, movement, and cognition. However, these shifts are highly individual. Genetics, health status, lifestyle, and environment all influence how nervous system changes manifest. Physical activity, cognitive engagement, and social interaction have been shown to support nervous system function across the lifespan. These activities influence blood flow, growth factor release, and synaptic maintenance. Importantly, engagement does not need to be intense. Consistency matters more than intensity. Gentle, regular activity supports neural health. Sleep and rest also play a role in nervous system adaptation. During rest, neural activity patterns shift, supporting maintenance and integration. This allows the system to consolidate changes that occurred during waking hours. Another key factor in lifelong nervous system development is emotional experience. Emotional responses involve coordinated activity across multiple neural systems. Repeated emotional patterns influence how these systems respond over time. For example, repeated exposure to certain types of stress can shape neural responses to future challenges. Conversely, repeated exposure to supportive, predictable environments can promote stability and resilience. This does not mean that early experiences permanently determine outcomes. Later experiences can modify neural patterns. However, early patterns can influence how readily the system responds to change. The nervous system also adapts to physical changes in the body. Changes in muscle strength, joint flexibility, and sensory acuity alter the information available to the nervous system. In response, neural circuits adjust how they interpret and act on this information. This ongoing recalibration supports coordination and balance even as the body changes. Another important fact is that the nervous system is sensitive to cumulative effects. Small changes over time can add up. Repeated patterns of activity, rest, engagement, and challenge influence long-term function. This cumulative nature means that no single day or experience defines nervous system health. Patterns over weeks, months, and years matter more. It also means that gradual changes can be supported through gradual adjustments. There is rarely a need for abrupt or extreme interventions. The nervous system's relationship with learning also changes over time. Older adults may rely more on meaningful learning rather than rote repetition. Learning that connects to existing knowledge or personal relevance tends to be more effective. This reflects efficient use of established neural networks. New information is integrated into existing frameworks rather than stored in isolation. Another important aspect of lifespan adaptation is emotional regulation. With age and experience, many people develop improved emotional regulation, even as certain cognitive processes slow. This reflects shifts in neural prioritization. The nervous system may become more selective about what it responds strongly to, based on accumulated experience. This selectivity can support stability and well-being. However, this is not universal. Individual differences are substantial. Health conditions, stress exposure, and environment all play a role. One of the most important facts to emphasize is that nervous system aging is not a single, uniform process. Different regions and systems change at different rates. Some functions remain stable or even improve, while others decline gradually. Understanding this variability helps avoid overly simplistic narratives about aging. Change does not equal loss across the board. It reflects reorganization. As we continue, we'll look more closely at how the nervous system interacts with long-term health, how chronic conditions influence neural regulation, and how the system responds to ongoing demands over decades. For now, allow this perspective to settle. The nervous system is not a fragile structure waiting to fail. It is a dynamic system shaped by time, experience, and adaptation. As this exploration continues, it may become clearer that the nervous system is shaped not only by age, but by what it is repeatedly exposed to over time. Experiences leave traces. Some are brief and fade quickly. Others accumulate gradually, influencing how the system responds long after the original experience has passed. One of the most significant influences on nervous system function across the lifespan is long-term stress. In physiological terms, stress refers to any demand that requires the body to adjust. This includes physical demands, emotional challenges, illness, environmental changes, and sustained uncertainty. The nervous system is well equipped to handle short-term stress. When a challenge arises, neural circuits coordinate increased alertness, energy mobilization, and focused attention. Once the challenge passes, regulatory mechanisms help the system return toward baseline. Problems arise when stress responses are activated frequently or remain engaged for long periods without adequate recovery. Chronic stress does not mean constant crisis. It often takes quieter forms: ongoing worry, persistent responsibility, unresolved conflict, financial uncertainty, caregiving demands, or long-standing health concerns. These conditions may not feel dramatic, but they place continuous demands on nervous system regulation. Over time, repeated activation of stress-related circuits can alter how the nervous system calibrates itself. Baseline levels of arousal may increase. Thresholds for activation may lower. Recovery may take longer. These changes are adaptive in the short term. They prepare the system to respond quickly in demanding environments. But when sustained, they can reduce flexibility. Importantly, these changes are not signs of damage. They are signs of learning. The nervous system is responding to patterns it detects in the environment. Another important factor influencing nervous system function over time is health status. Chronic health conditions, such as cardiovascular disease, metabolic disorders, inflammatory conditions, and respiratory issues, can all interact with neural regulation. For example, changes in blood flow can affect oxygen and nutrient delivery to neural tissue. Metabolic imbalances can influence neurotransmitter synthesis and signaling. Inflammatory signals can alter neural excitability. These interactions are bidirectional. The nervous system influences bodily systems, and bodily systems influence the nervous system. This reciprocal relationship means that changes in one area can ripple across others. This complexity is why nervous system function cannot be understood in isolation. It reflects the state of the entire organism. Another key influence is medication. Many medications affect nervous system signaling directly or indirectly. Some act on neurotransmitter systems. Others influence blood pressure, heart rate, or metabolic processes, which in turn affect neural regulation. Medication effects can be beneficial, neutral, or sometimes challenging. The nervous system often adapts over time, adjusting receptor sensitivity or signaling patterns in response to ongoing exposure. This adaptation explains why medication effects can change over time and why adjustments may be needed. It also highlights the importance of individualized approaches to treatment. Environmental factors also play a significant role. Light exposure, noise levels, temperature, and air quality all influence nervous system activity. Consistent environments allow the system to predict conditions and regulate efficiently. Highly variable or chaotic environments require constant adjustment. Social environment matters as well. Social interaction engages multiple neural systems involved in communication, emotion, and regulation. Supportive social contact can stabilize neural activity, while isolation can alter regulatory patterns. However, quality matters more than quantity. Meaningful interaction has a different neural impact than superficial contact. Another important long-term influence is cognitive engagement. Activities that involve attention, problem-solving, creativity, or learning stimulate neural circuits and support synaptic maintenance. This engagement does not need to be complex or demanding. Activities such as reading, conversation, music, and gentle learning can be sufficient. The nervous system responds best to moderate challenge, followed by recovery. Excessive challenge without rest can be taxing. Too little challenge can lead to understimulation. Balance matters. Physical movement is also deeply intertwined with nervous system health. Movement provides sensory feedback, supports circulation, and engages motor and regulatory circuits. Even gentle movement influences neural signaling. Importantly, movement does not need to be strenuous to be beneficial. Walking, stretching, and routine physical activity provide valuable input to the nervous system. Another factor influencing long-term nervous system function is predictability. Predictable routines reduce uncertainty and lower regulatory demands. When the system can anticipate what comes next, it expends less energy monitoring for surprise. This does not mean life should be rigid. Variation within a predictable framework is often optimal. The nervous system benefits from knowing the general shape of the day while remaining flexible within it. Unpredictability, especially when combined with lack of control, increases regulatory load. Over time, this can influence baseline arousal levels. The nervous system also adapts to patterns of attention, where attention is repeatedly directed influences which neural circuits are reinforced. Sustained focus on threat, uncertainty, or negative outcomes can strengthen related networks. Sustained focus on neutral or meaningful activities can strengthen others. This does not mean that difficult thoughts should be suppressed. It means that repeated patterns matter. Another important long-term influence is sleep and rest patterns. Rest is not merely absence of activity. It involves active neural processes that support maintenance and integration. During rest, certain neural networks reduce activity while others increase. This redistribution supports repair, synaptic maintenance, and recalibration of regulatory systems. Chronic disruption of rest can influence nervous system regulation, but the system often adapts. It may alter timing, intensity, or distribution of rest processes rather than eliminating them. This adaptability is a recurring theme. The nervous system rarely stops functioning. It shifts how functions are expressed. Another factor shaping nervous system function over time is emotional learning. Emotional responses are not fixed traits. They are patterns shaped by repeated experience. For example, repeated exposure to manageable challenges can strengthen regulatory capacity. Repeated exposure to overwhelming situations without support can sensitize stress responses. These patterns are not permanent. Later experiences can modify them. However, modification often occurs gradually. The nervous system also responds to meaning. Experiences perceived as meaningful engage different neural circuits than experiences perceived as arbitrary or threatening. Meaning can buffer stress response and support regulation. This helps explain why purpose, engagement, and personal relevance influence nervous system health. Another important point is that nervous system adaptation is context-specific. The same individual may show different regulatory patterns in different environments. Familiar settings may support calm regulation. Novel or demanding settings may increase activation. This flexibility allows adaptation, but can also create contrast. A person may feel very different depending on context, reflecting changes in neural regulation rather than stable traits. Over decades, these influences accumulate. The nervous system reflects a history of adaptation to specific patterns of demand, support, and environment. This history does not dictate the future, but it influences starting points. Understanding this can reduce self-blame. Many regulatory patterns are learned responses to past conditions. The nervous system also responds to gradual change better than abrupt change. Sudden alterations in routine, environment, or health status can temporarily challenge regulation. Over time, adaptation usually occurs. This is why transitions, retirement, relocation, illness, loss, can temporarily affect nervous system function. The system must recalibrate to new conditions. Recalibration takes time. It is not immediate. Another important fact is that nervous system regulation is probabilistic rather than precise. Responses are based on likelihoods rather than certainties. This means variability is normal. On some days, regulation may feel smooth. On others, less so. These fluctuations reflect ongoing adjustment rather than instability. This probabilistic nature also means that single experiences rarely define outcomes. Patterns over time matter more. The nervous system also uses learning to conserve energy. Once patterns are established, responses become more automatic. This efficiency is beneficial, but it can also make change slower. Change often requires repeated exposure to new patterns under manageable conditions. Abrupt forcing tends to increase resistance. This principle applies across the lifespan. Another factor influencing nervous system function is sensory change. Vision, hearing, touch, and proprioception may shift with age or health. The nervous system adapts by reweighting sensory input. For example, if visual input becomes less reliable, proprioceptive or auditory input may become more influential. This reweighting supports continued function. This process illustrates how the nervous system prioritizes function over fidelity. It uses available information to maintain behavior rather than insisting on perfect input. The nervous system also responds to cumulative fatigue. Fatigue is not just muscular or cognitive. It reflects regulatory load across systems. Periods of sustained demand without recovery increase fatigue. Recovery restores regulatory capacity. Without adequate recovery, baseline regulation may shift. This again highlights the importance of balance. Another important influence is inflammation. Low-grade inflammation, common with aging and certain health conditions, can influence neural signaling. It may alter neurotransmitter systems and neural excitability. These effects are typically subtle and gradual. They interact with other factors rather than acting alone. The nervous system responds by adjusting signaling thresholds and patterns. This adaptation may influence sensitivity, mood, or energy levels. Importantly, these changes do not indicate failure. They reflect ongoing interaction between systems. As we continue through this exploration, a pattern emerges. The nervous system is not static, fragile, or easily broken. It is responsive, adaptive, and shaped by long-term patterns. Understanding this shifts perspective. Experiences are not simply good or bad for the nervous system. They are inputs that influence adaptation. So, we continue. It may become clearer that later adulthood is not defined by a single direction of change in the nervous system. Instead, it is defined by redistribution. Certain processes slow, others become more efficient, and priorities shift. The system reorganizes itself based on decades of accumulated experience. One of the most consistent findings in neuroscience is that the aging nervous system becomes more selective. Rather than responding equally to all stimuli, it prioritizes what is proven relevant over time. This selectivity is not a limitation. It is a strategy for conserving energy and maintaining stability. Attention, for example, often becomes more focused on meaningful or familiar information. Novel or irrelevant stimuli may be filtered more strongly. This can support emotional regulation and decision-making, even if it reduces responsiveness to less important input. Emotional processing also changes with age. Many older adults show reduced reactivity to negative stimuli and greater stability in emotional response. This is sometimes referred to as the positivity effect, where attention and memory increasingly favor neutral or positive information. This shift is associated with changes in neural networks linking emotional centers of the brain, with regions involved in regulation and interpretation. Experience appears to strengthen top-down modulation, allowing emotional responses to be contextualized more effectively. This does not mean that negative emotions disappear. It means that the nervous system may become better at containing them without escalation. Another important adaptation in later adulthood is reliance on predictive processing. The nervous system increasingly uses prior knowledge to interpret sensory input. This allows efficient functioning even when sensory signals become noisier or less precise. For example, familiar environments are navigated more easily than unfamiliar ones. The nervous system fills in gaps using memory and expectation. This predictive strategy reduces cognitive load and supports smooth behavior. This reliance on prediction also explains why sudden changes in environment or routine can feel more challenging. When predictions no longer match input, the system must update its models, which requires additional effort. Given time and repeated exposure, new predictions form, and regulation stabilizes again. Motor control also reflects redistribution rather than simple decline. While raw reaction speed may decrease, movement often becomes more deliberate and economical. The nervous system emphasizes accuracy and safety over speed. This shift reduces risk and supports long-term function. It reflects adaptation to changing physical conditions rather than loss of control. Coordination remains highly plastic. With continued movement and practice, neural circuits supporting balance and posture can remain robust. Another key change involves sensory integration. As individual sensory modalities change, the nervous system adjusts how it weights information. Vision, proprioception, vestibular input, and touch are integrated differently depending on reliability. This adaptive reweighting allows stable perception and movement, even when one source of input becomes less precise. Cognitive processing also shows redistribution. While some aspects of processing speed decline, others, such as vocabulary, pattern recognition, and contextual reasoning, remain stable or improve. These changes reflect shifts in which neural networks are most active. Experience-rich networks become more influential, while rapid response systems may be used more selectively. Memory systems also change. Working memory capacity may decrease slightly, while long-term memory remains strong. Emotional and semantic memories are often well preserved. The nervous system compensates by relying more on established memory structures and less on rapid manipulation of new information. Another important factor is that neural noise may increase slightly with age. Neural signaling can become less precise at the micro level. However, at the network level, the nervous system often compensates by averaging across signals and relying on redundancy. This compensation supports stable function despite increased variability at smaller scales. Variability itself becomes a key concept. Healthy aging nervous systems often show greater moment-to-moment variability, but maintain overall stability. This flexibility allows adaptation across conditions. Rigidity, rather than variability, is often associated with reduced adaptability. Another notable change in later adulthood is altered sensitivity to internal signals. Interoception, the sensing of internal bodily states, may become more prominent. Heartbeat, breathing, and bodily sensations may be noticed more readily. This increased awareness reflects changes in neural processing and attention rather than pathology. It can influence emotional experience and decision-making. The nervous system also becomes more influenced by context. Familiar routines support efficient regulation. Disruption of routines can temporarily increase regulatory demands. This is why transitions can feel more challenging. The system must update predictive models and recalibrate responses. However, once new routines are established, regulation often stabilizes again. Another important adaptation involves energy allocation. The nervous system becomes more conservative. It prioritizes essential functions and meaningful engagement over unnecessary activation. This conservation supports resilience. It allows the system to function effectively with fewer resources. This shift may be experienced subjectively as a preference for quieter environments, fewer simultaneous demands, or more predictable routines. These preferences reflect regulatory optimization rather than decline. The nervous system also shows increased coupling between emotional and cognitive regulation. Decisions may be guided more by values and long-term meaning rather than immediate reward. This reflects changes in how neural networks interact. Experience shapes priorities. Another important factor is recovery time. While the nervous system remains capable of adaptation, recovery from intense demands may take longer. This is not because recovery mechanisms fail, but because regulatory thresholds shift, allowing adequate recovery supports continued adaptation. This, again, highlights that balance becomes more important than intensity. Another key concept is that aging nervous systems often benefit from rhythm. Regular cycles of activity and rest support regulation. Predictable patterns reduce uncertainty and conserve energy. Rhythm supports both stability and flexibility. Within a rhythmic framework, variation is easier to tolerate. Another important adaptation is increased reliance on social and environmental scaffolding. External supports, routines, reminders, familiar spaces work in partnership with neural processes. Using such supports is not a sign of weakness. It is a strategy for optimizing function. The nervous system has always relied on environment. This reliance becomes more visible with age. Another significant point is that nervous system aging is highly individual. Genetics, health history, education, occupation, social engagement, and environment all influence trajectories. There is no single pattern of normal aging. Variation is the norm. Understanding this variability reduces unhelpful comparison. Each nervous system reflects a unique history of adaptation. The nervous system also responds to meaning and purpose throughout life. Engagement with meaningful activities supports neural networks involved in motivation and regulation. Meaningful engagement does not require intensity. Consistency matters more. Another important adaptation is that the nervous system becomes better at distinguishing signal from noise. Experience allows it to ignore irrelevant fluctuations and focus on what matters. This selectivity supports emotional stability and decision-making. However, it can also reduce tolerance for chaotic environments. This reflects optimization rather than fragility. As we approach the end of this part, a central theme becomes clear. Later adulthood involves reorganization rather than decline. The nervous system adjusts strategies to maintain function in changing conditions. This reorganization supports resilience, stability, and continuity of identity. As this section comes toward completion, it may help to step back and notice a broader pattern. Across decades, the nervous system does not simply wear down. It reorganizes itself in response to what life repeatedly asks of it. Stability emerges not from sameness, but from continual adjustment. One of the most important long-term adaptations of the nervous system is coherence. Coherence refers to how well different parts of the system work together. Even when individual components change, coordinated interaction can preserve overall function. In later adulthood, coherence often becomes more important than speed or intensity. Neural systems prioritize communication efficiency, timing, and integration. This supports stable behavior, even as underlying mechanisms shift. Coherence is supported by experience. Decades of interacting with the world allow the nervous system to recognize patterns quickly and respond appropriately without excessive processing. This reduces cognitive load and conserves energy. Another critical aspect of long-term adaptation is recalibration of thresholds. Thresholds determine how much input is required to trigger a response. Over time, these thresholds may shift based on repeated experience. For example, the amount of stimulation needed to capture attention may increase, while the threshold for detecting meaningful changes may remain low. This selective sensitivity allows the nervous system to remain responsive without being overwhelmed. Recalibration also applies to emotional responses. Situations that once triggered strong reactions may no longer do so, while genuinely significant events continue to register. This does not mean emotional flattening. It means refinement. Another important factor is consolidation. Over time, frequently used neural pathways become deeply established. These pathways support habits, skills, and identity. Consolidation provides continuity across change. This continuity allows a person to remain recognizably themselves, even as circumstances evolve. The nervous system preserves core patterns while allowing peripheral adjustments. At the same time, consolidation can make change slower. Deeply established patterns require repeated experience to modify. This does not mean change is impossible. It means it is gradual. Gradual change aligns with how the nervous system prefers to adapt. Another long-term adaptation involves prioritization of internal signals. With age and experience, the nervous system often places greater emphasis on internal feedback rather than external cues alone. This internal orientation supports self-regulation. Decisions may be guided more by internal states and long-term considerations than by immediate external pressures. This shift can influence behavior, preferences, and pacing. It reflects adaptive recalibration rather than withdrawal. Another important aspect of long-term nervous system function is energy management. Neural processing is energetically costly. Over time, the system becomes more economical, reducing unnecessary activation. This economy may be experienced as a preference for fewer simultaneous demands, quieter environments, or more focused engagement. These preferences support sustainable regulation. Economy does not mean reduced capacity. It means optimized use of available resources. Another factor shaping long-term adaptation is resilience. Resilience refers to the ability to absorb disturbance and return toward baseline. It does not mean avoiding disturbance. The nervous system builds resilience through repeated cycles of challenge and recovery. Recovery is as important as challenge. Without recovery, adaptation becomes strained. In later adulthood, recovery may require more time. This reflects shifts in regulatory dynamics rather than failure. Allowing adequate recovery supports resilience. Another important long-term adaptation involves integration of emotional experience. Over time, emotional responses become more contextualized. Past experience informs present interpretation. This integration supports emotional stability. Responses are shaped by understanding rather than immediacy alone. The nervous system learns which signals warrant strong response and which can be allowed to pass with minimal activation. Another significant adaptation is tolerance for ambiguity. With experience, the nervous system may become less reactive to uncertainty, not because uncertainty disappears, but because it has been encountered before. This tolerance supports calm decision-making and reduces unnecessary activation. However, tolerance varies by individual and context. It reflects learning rather than fixed capacity. Another key point is that long-term adaptation is influenced by narrative. The stories a person tells about their experiences shape neural interpretation. If experiences are framed as survivable and meaningful, regulatory systems respond differently than if experiences are framed as overwhelming or threatening. Narrative influences expectation, and expectation influences regulation. This highlights the importance of perspective in nervous system function. Another important aspect of long-term nervous system health is maintenance of connectivity. Connectivity refers to how well different regions communicate. Even as individual connections change, overall connectivity can remain robust through redundancy and alternative pathways. This connectivity supports integration across cognitive, emotional, and physical domains. Another long-term adaptation involves calibration of motivation. Motivation systems may shift focus from novelty-seeking to meaning-oriented engagement. This reflects changes in neural reward systems and valuation. Meaningful engagement continues to activate motivation circuits even as preferences evolve. Another important point is that nervous system adaptation is ongoing until the end of life. There is no final stable state where change stops. Even late in life, neural systems continue to adjust to conditions, experiences, and internal signals. This continuous adaptation supports dignity and agency across the lifespan. Another key aspect is that nervous system health cannot be reduced to isolated metrics. It reflects patterns of interaction across systems, contexts, and time. Single measures rarely capture this complexity. Understanding this complexity helps avoid oversimplified conclusions about function or decline. As we complete this section, it becomes clear that long-term nervous system adaptation is not about resisting change. It is about reorganizing in ways that preserve coherence, function, and identity. Change is not the opposite of stability. It is the mechanism through which stability is maintained. As we move into this next section, the focus shifts from long stretches of time to what happens right now, moment by moment. The nervous system is not only shaped across years and decades, it is also continuously active in the present, coordinating awareness, sensation, and response in real time. At every moment, the nervous system is balancing two fundamental tasks. One is monitoring the internal state of the body. The other is monitoring the external environment. These tasks happen simultaneously, and most of the time, they happen outside of conscious awareness. Internal monitoring involves signals from within the body. These include information about heart rate, breathing, blood pressure, digestion, temperature, muscle tension, and chemical balance. This stream of information is known as interoception. It allows the nervous system to track the condition of the body and adjust regulation accordingly. External monitoring involves sensory input from the environment. Light, sound, touch, movement, and spatial orientation are continuously sampled. This information allows the nervous system to detect opportunities, changes, and potential challenges. The integration of internal and external information is one of the nervous system's most important functions. It allows responses to be appropriate rather than reflexive. For example, the same sound may be ignored in a familiar environment, but prompt attention in an unfamiliar one. Context matters. Attention plays a central role in this process. Attention is not simply a spotlight that illuminates information. It is a dynamic, filtering system. It determines which signals are amplified and which are dampened. At any moment, countless signals compete for processing. The nervous system prioritizes those that are relevant, novel, or emotionally significant. This prioritization occurs through coordinated activity across multiple brain regions, including the thalamus, brainstem, and cortex. Attention can be directed voluntarily, such as when reading or listening closely. It can also be captured automatically by salient stimuli, such as sudden movement or sound. These two modes interact continuously. Importantly, attention is limited. The nervous system cannot process everything with equal depth at once. This limitation is not a flaw. It is a design feature that prevents overload. Moment-to-moment regulation depends on this selective processing. By limiting what enters conscious awareness, the nervous system maintains stability and efficiency. Another key process operating in real time is sensory integration. Sensory information does not arrive as a unified package. Each sensory system operates with its own timing and characteristics. The nervous system must align and integrate these signals to create a coherent experience. For example, when speaking with someone, visual cues from facial expression, auditory cues from voice, and proprioceptive cues from posture are combined. This integration allows understanding beyond the words alone. Timing is crucial here. Slight delays between sensory inputs are normal, but the nervous system adjusts for them automatically. This temporal alignment supports seamless perception. The nervous system also continuously adjusts sensitivity. Sensory gain, the degree to which signals are amplified, changes based on context. In quiet environments, sensitivity increases. In noisy environments, sensitivity decreases. This dynamic adjustment allows perception to remain useful across varying conditions. Another important moment-to-moment function is prediction error processing. The nervous system is constantly comparing incoming information to predictions based on prior experience. When information matches prediction, processing is efficient. When it does not, attention increases. This difference between expectation and input is known as prediction error. Prediction errors signal the need for learning or adjustment. Small prediction errors are common and usually resolved quickly. Large or persistent prediction errors demand more resources and may shift attention or behavior. This predictive framework allows the nervous system to operate efficiently. It does not need to analyze every detail if the environment is familiar and predictable. Moment-to-moment awareness is shaped by this balance between prediction and input. Much of what feels immediate and present is actually filtered and interpreted through expectation. Another real-time process is regulation of arousal. Arousal level influences how responsive the nervous system is. Low arousal reduces sensitivity and slows processing. High arousal increases sensitivity and readiness. The nervous system adjusts arousal continuously based on internal state and external demands. This adjustment is mediated by brainstem networks and neuromodulatory systems. Importantly, arousal is not the same as emotion. It refers to general activation level. Emotion involves specific patterns of activation across networks. Moment-to-moment regulation involves keeping arousal within an optimal range for the situation. Too little arousal impairs responsiveness. Too much impairs precision. This balance is dynamic. It shifts as demands change. Another important real-time function is motor readiness. Even when still, the nervous system maintains a state of readiness for movement. Muscles are not fully relaxed. Postural control systems remain active. This readiness allows rapid response when needed. It also supports balance and stability. Motor readiness is modulated continuously based on context. In safe, familiar environments, readiness may be lower. In uncertain or demanding environments, it may increase. Another moment-to-moment process is emotional appraisal. Incoming information is evaluated for significance. This appraisal happens rapidly and often unconsciously. Emotional appraisal influences attention, memory encoding, and physiological response. It is not a separate step added after perception. It is integrated into perception itself. This integration allows quick, context-appropriate responses. Moment-to-moment nervous system activity also includes maintenance processes. Neural networks involved in default monitoring, memory integration, and self-referential processing remain active even when external demands are low. These networks support continuity of experience and identity. The nervous system also manages transitions. Shifts between activities, thoughts, or environments require recalibration. The system adjusts attention, arousal, and motor readiness to accommodate change. Transitions are moments of increased regulatory demand. Smooth transitions reduce load. Abrupt transitions increase it. Understanding this helps explain why sudden interruptions can feel disruptive. Another key aspect of real-time function is noise management. Neural signaling is inherently variable. The nervous system uses averaging, inhibition, and redundancy to reduce noise and extract meaningful signals. This noise management supports stability. It allows reliable perception and action, despite variability at the cellular level. Moment-to-moment regulation also involves prioritizing internal maintenance. When resources are limited, the nervous system may reduce responsiveness to external input to support internal processes. This prioritization reflects adaptive regulation. Another important real-time function is learning at the micro level. Even within a single interaction, neural connections can adjust slightly. These micro-adjustments accumulate over time. This allows continuous fine-tuning without conscious effort. The nervous system also monitors outcomes. Actions are evaluated based on their effects. This feedback influences subsequent behavior. This evaluation happens quickly and often outside awareness. Moment-to-moment function is therefore not static. It is a continuous loop of sensing, predicting, acting, and updating. Understanding this loop helps reframe experience. Many fluctuations in attention, sensation, or responsiveness reflect normal regulatory adjustments rather than problems. As we continue, we'll look more closely at how attention itself is structured, how focus shifts, and how awareness is shaped by neural processes in everyday life. For now, allow this description of real-time function to remain open-ended. Like the processes it describes, it is ongoing, fluid, and adaptive. As we continue, attention becomes a useful place to linger, because attention is one of the most noticeable expressions of nervous system activity. It is also one of the most misunderstood. Attention is often treated as something a person either has or lacks, but in reality, it is a process that is continuously shaped by neural regulation, context, and internal state. Attention does not arise from a single location in the brain. It emerges from coordinated activity across multiple systems. Brainstem networks regulate overall alertness. Thalamic circuits control the flow of sensory information. Cortical regions help direct focus and interpret meaning. Together, these systems determine what enters awareness and how strongly it is experienced. At any given moment, attention is divided between external and internal sources. External attention is directed towards sights, sounds, and events in the environment. Internal attention is directed toward thoughts, memories, sensations, and feelings. The nervous system shifts between these modes continuously. These shifts often happen without conscious choice. A sound may draw attention outward. A thought may pull attention inward. The nervous system prioritizes based on relevance, novelty, and emotional significance. This means that wandering attention is not a failure of control. It is a sign that the nervous system is monitoring multiple streams of information and reallocating resources as needed. Another important aspect of attention is that it operates at different depths. Some information is processed shallowly, enough to register presence without detailed analysis. Other information is processed deeply, engaging memory, emotion, and interpretation. The depth of processing depends on context and demand. Routine information may be processed lightly. Novel or meaningful information may be processed deeply. This selective depth allows efficiency. The nervous system does not expend equal energy on everything. Perception itself is shaped by attention. What is attended to is perceived more clearly. What is not attended to may be filtered out entirely. This filtering happens early in sensory processing, not only at conscious levels. For example, visual information outside the focus of attention may not be encoded in detail, even if it falls on the retina. Auditory information may be ignored if deemed irrelevant. This does not mean that unattended information has no effect. It may influence behavior subtly or be processed unconsciously, but it does not dominate awareness. Another important point is that attention is influenced by expectation. The nervous system prepares to detect what it expects to find. This preparation biases perception. For example, when searching for something specific, related stimuli are detected more readily. This reflects predictive modulation of sensory processing. Expectation allows faster detection, but can also lead to overlooking unexpected information. This trade-off is part of efficient processing. Attention is also influenced by emotional state. Emotional significance increases attentional priority. Stimuli associated with past emotional experience are more likely to capture attention. This prioritization reflects learning. The nervous system remembers which signals have mattered before. Another key factor shaping attention is fatigue. When regulatory resources are taxed, attention becomes narrower and less flexible. The nervous system reduces the scope of monitoring to conserve energy. This narrowing is adaptive in the short term. It allows essential functions to continue when resources are limited. However, prolonged fatigue can reduce attentional flexibility. Recovery restores capacity. Attention also fluctuates rhythmically. Neural oscillations influence when information is most likely to be processed. Attention is not constant, even within seconds. It pulses. These fluctuations are subtle and usually unnoticed. They allow sampling of the environment without continuous high-cost processing. Another important aspect of attention is that it is trainable, but not in the sense of forceful control. Attention adapts through repeated patterns of engagement. When attention is repeatedly directed toward certain types of information, related neural networks strengthen. This makes future attention shifts more likely. This does not require effortful control. It occurs through exposure and repetition. Another point often overlooked is that attention is influenced by posture and movement. Body position affects sensory input and neural signaling. Upright posture, movement, and stillness all influence attentional patterns. This reflects the integration of sensory and motor systems. Attention is embodied. The nervous system also uses attention to regulate emotional response. Directing attention away from emotionally intense stimuli can reduce response magnitude. Directing attention toward contextual information can support regulation. These processes often happen automatically rather than deliberately. Another key element of attention is its relationship with memory. Attention determines what is encoded into memory. Information that is not attended to is less likely to be remembered. This is why emotionally or personally significant events are often remembered more vividly. Attention was strongly engaged. Memory, in turn, influences attention by shaping expectations and priorities. This reciprocal relationship supports learning and adaptation. Attention is also shaped by social context. The presence of others influences what is attended to and how. Facial expressions, tone of voice, and social cues are processed rapidly and often prioritized. This social sensitivity reflects the nervous system's adaptation to group living. Another important aspect is divided attention. The nervous system can process multiple streams of information, but only to a limited extent. Dividing attention reduces processing depth. This limitation is not a flaw. It reflects energy constraints. When multiple demands compete, the nervous system prioritizes based on urgency and relevance. Another factor shaping attention is novelty. Novel stimuli are more likely to capture attention because they signal potential change. However, novelty loses its effect with repetition. This habituation allows attention to shift away from familiar, non-threatening stimuli. Attention also plays a role in the sense of time. When attention is engaged, time may feel compressed. When attention is diffuse or focused on internal states, time may feel expanded. This subjective experience reflects how neural resources are allocated. Another important point is that attention is not continuous. There are brief lapses even during focused activity. These lapses are normal and reflect the nervous system's need to sample and recalibrate. Attempting to eliminate lapses entirely increases regulatory load. Allowing natural fluctuation supports sustainability. Another key element is that attention is influenced by meaning. Meaningful stimuli engage attention more readily than arbitrary ones. This engagement reflects motivational systems. Meaning does not need to be dramatic. Personal relevance is sufficient. The nervous system prioritizes what matters. As this part comes toward a pause, it becomes clear that attention is not a simple skill to be controlled. It is a dynamic process shaped by neural regulation, context, experience, and internal state. Understanding attention in this way can change how fluctuations are interpreted. Variability is not failure. It is regulation in motion. As we continue, perception becomes the natural next place to rest our attention. Perception feels immediate and obvious. It feels like a direct window onto the world. Yet perception is one of the most carefully constructed experiences produced by the nervous system. Perception is not a passive recording of sensory input. It is an active process of interpretation. The nervous system receives raw signals, patterns of light, pressure, vibration, and chemical change, and transforms them into meaningful experience. What you perceive is the result of this transformation. At the most basic level, sensory receptors convert physical energy into neural signals. Light striking the retina becomes electrical activity in visual neurons. Sound waves moving the inner ear become patterns of neural firing. Pressure on the skin becomes signals carried by touch receptors. These signals are only the beginning. On their own, they do not contain meaning. Meaning arises through processing. The nervous system organizes sensory input hierarchically. Early processing stages extract basic features: edges, contrast, pitch, intensity. Later stages integrate these features into patterns, objects, and relationships. Still later stages connect perception with memory, emotion, and expectation. This layered processing allows perception to be both efficient and flexible. It also means that perception is influenced by more than just incoming signals. Expectation plays a powerful role. The nervous system constantly predicts what it is likely to perceive based on context and past experience. Incoming sensory input is compared against these predictions. When input matches expectation, perception feels smooth and immediate. When it does not, attention increases. This predictive process explains why familiar environments feel stable and easy to navigate. The nervous system already knows what to expect, so it fills in details efficiently. It also explains why perception can be fooled. When expectations are strong, they can override ambiguous input. Optical illusions demonstrate this clearly, but the same principle applies to everyday experience. Perception is therefore a collaboration between input and expectation. Neither alone determines experience. Another important aspect of perception is that it is multisensory. The nervous system integrates information from different senses to create a unified experience. Vision influences how sound is perceived. Touch influences how movement is felt. Balance information influences spatial perception. This integration increases reliability. When one sensory signal is ambiguous, others can clarify it. It also means that changes in one sensory system can influence overall perception. For example, changes in vision can alter balance perception. Changes in hearing can affect spatial awareness. The nervous system adapts to these changes by reweighting sensory input. If one sense becomes less reliable, others are given more influence. This reweighting supports continuity of perception. Perception is also shaped by bodily state. Internal signals influence how external input is interpreted. For example, fatigue can reduce sensory sensitivity. Arousal can amplify it. Emotional state also influences perception. Neutral stimuli may be perceived differently depending on emotional context. This is not distortion. It is prioritization. The nervous system highlights information relevant to current needs. Another important point is that perception is temporally integrated. Sensory input arrives continuously, but perception is smoothed over time. The nervous system averages input across brief windows to reduce noise. This smoothing supports stability. Without it, perception would feel jittery and fragmented. However, smoothing also means the perception lags slightly behind real-time input. This delay is usually unnoticed because prediction fills the gap. Perception is therefore always slightly behind reality, yet feels immediate. This apparent paradox reflects the efficiency of predictive processing. Another key aspect of perception is figure ground organization. The nervous system separates what is relevant from what is background. This allows focus. What is considered figure and what is background can change depending on attention, context, and meaning. The same sensory input can be perceived differently depending on what the nervous system prioritizes. This flexibility supports adaptation. Perception is also influenced by learning. With experience, the nervous system becomes better at detecting meaningful patterns. Experts in a field perceive details that novices miss, even though the sensory input is the same. This expertise reflects changes in neural networks that guide interpretation. Another important aspect is that perception is embodied. It is influenced by posture, movement, and action. How you move influences what you perceive. Perception and action form a loop. For example, reaching toward an object changes how it is perceived. The nervous system anticipates sensory consequences of movement and adjusts perception accordingly. This sensoromotor integration allows coordination and accuracy. Perception also involves memory. Memory provides context that shapes interpretation. Without memory, sensory input would lack continuity. This continuity allows recognition. You know an object is the same object across different views because memory links those views. Perception is therefore inseparable from memory. Another key point is that perception varies across individuals. Differences in sensory sensitivity, experience, and neural organization mean that people perceive the same environment differently. These differences are not errors. They reflect individual nervous system histories. Perception also changes across the lifespan. Sensory thresholds may shift. Integration strategies may adapt. Prediction may play a larger role. These changes reflect adaptation rather than failure. Another important concept is that perception is resource dependent. When regulatory resources are limited, perception becomes less detailed. The nervous system prioritizes essential features. This prioritization supports survival and function under constraint. Perception also involves emotional coloring. Emotional significance influences how vividly stimuli are perceived and remembered. This coloring helps prioritize what matters. The nervous system uses emotion to guide perception, not to distort it arbitrarily. Another aspect of perception is that it can be influenced by language and concepts. Labels shape how stimuli are categorized and remembered. This influence reflects top-down modulation. However, basic perception occurs before language. Language refines rather than creates perception. Perception also adapts to context rapidly. Entering a dark room, sensitivity adjusts. Entering a noisy environment, auditory filtering increases. These adjustments reflect automatic regulation. Another important point is that perception is probabilistic. The nervous system selects the most likely interpretation given available information. This selection is usually accurate, but not guaranteed. Errors occur when information is ambiguous or predictions are mismatched. These errors are a cost of efficiency. The nervous system accepts this cost because perfect accuracy would require unsustainable resources. Understanding perception as probabilistic helps reframe occasional misperceptions. They're not signs of malfunction, but trade-offs. Perception also plays a role in the sense of self. Awareness of body boundaries, position, and internal state contributes to a continuous sense of identity. This bodily self is constructed moment by moment through sensory integration. Changes in perception can influence this sense of self. However, the nervous system usually maintains continuity through integration and prediction. As we pause here, a broader understanding emerges. Perception is not something that happens to the nervous system. It is something the nervous system actively creates. This creation is shaped by input, expectation, memory, emotion, and bodily state. Understanding this does not make perception less real. It makes it more meaningful. As we move gently into this next part, awareness itself comes into focus. Awareness is often treated as something separate from the nervous system, almost like an observer standing apart from bodily processes. Yet awareness is not outside the system. It is one of the nervous system's most integrated functions. Awareness refers to the feeling of being present, of having experience at all. It includes awareness of the environment, awareness of the body, and awareness of thoughts and emotions. These forms of awareness are not produced by a single structure. They emerge from coordinated activity across many neural systems. At the most basic level, awareness depends on arousal. Without a certain level of neural activation, awareness fades. This is why deep unconsciousness, anesthesia, or severe brain injury can eliminate awareness entirely. Arousal provides the foundation upon which awareness is built. However, arousal alone is not enough. Awareness also requires integration. Information from different sensory systems, memory networks, and emotional circuits must be brought together into a coherent whole. This integration allows experience to feel unified rather than fragmented. Several large-scale brain networks are involved in this process. One network supports attention to the external world. Another supports internal monitoring and self-related processing. These networks interact continuously, shifting dominance depending on context. When attention is focused outward, awareness centers on the environment. When attention turns inward, awareness centers on thoughts, memories, or bodily sensations. Most of the time, awareness moves fluidly between these modes. This movement is not random. It is regulated by neural signaling that reflects relevance and demand. Another important aspect of awareness is that it is limited. The nervous system cannot bring everything into awareness at once. Only a small fraction of neural activity becomes conscious experience. Most processing remains unconscious. This limitation is not a weakness. It allows efficiency. If all neural activity were conscious, awareness would be overwhelmed. The nervous system therefore selects what enters awareness based on priority. Priority is determined by novelty, relevance, emotional significance, and current goals. This selection process explains why some sensations are barely noticed, while others dominate experience. Awareness is also shaped by timing. Conscious experience unfolds in brief windows rather than as a continuous stream. These windows are integrated so smoothly that awareness feels continuous. Within each window, information is sampled, integrated, and interpreted. Between windows, slight gaps occur. These gaps are usually unnoticed. This rhythmic structure supports stability and flexibility. Another important fact is that awareness is influenced by prediction. Much of what feels present is partly anticipated. The nervous system fills in expected information to create continuity. This predictive filling allows awareness to feel smooth even when sensory input is incomplete or delayed. It also means that awareness can sometimes reflect expectation more than input. This is why imagination, memory, and perception can feel similar in some respects. Awareness is therefore not a direct mirror of the world. It is a constructed experience shaped by both input and expectation. Another aspect of awareness is the sense of agency, the feeling that actions are initiated by oneself. This feeling emerges when motor plans, sensory feedback, and prediction align. When actions unfold as expected, agency feels strong. When there is mismatch, agency can feel reduced or disrupted. This alignment happens automatically and usually outside awareness. Only when something goes wrong does the sense of agency come into focus. The sense of self is closely tied to awareness. The self is not a fixed entity located in one part of the brain. It is a dynamic pattern of activity involving memory, body representation, emotional processing, and narrative. This pattern provides continuity across moments. It allows experiences to to feel like they belong to the same person over time. The nervous system maintains this continuity through integration. Even as specific thoughts or sensations change, the underlying pattern persists. Another important point is that awareness is influenced by bodily signals. Internal sensations contribute to the feeling of being alive and present. Changes in breathing, heart rate, or posture can subtly shift awareness. This embodied nature of awareness means that mind and body are not separate domains. They are integrated aspects of nervous system function. Awareness is also influenced by emotion. Emotional significance increases the likelihood that information enters awareness. This prioritization supports survival and learning. However, emotional influence does not mean distortion. It means weighting. The nervous system highlights what matters. Another key aspect of awareness is that it can vary in clarity. Sometimes awareness feels vivid and focused. Other times, it feels diffuse or dull. These variations reflect changes in arousal, attention, and regulation. They are normal fluctuations rather than indicators of problem. Awareness also changes with fatigue, illness, and stress. When regulatory resources are limited, awareness may narrow. The nervous system conserves energy by reducing the scope of conscious processing. This narrowing is adaptive. It allows essential functions to continue. Another important fact is that awareness can include awareness of awareness itself. This meta-awareness allows reflection on experience. It involves additional neural integration. Meta-awareness is not constant. It comes and goes depending on context and demand. The nervous system does not maintain it continuously because it is resource-intensive. Awareness is also shaped by social context. The presence of others influences what is brought into awareness and how it is interpreted. Social cues are processed rapidly and often unconsciously. This social modulation reflects the nervous system's adaptation to interpersonal environments. Another key point is that awareness is not located in any single moment. It unfolds over time. Each moment of awareness depends on what came just before and influences what comes next. This continuity supports a stable sense of experience. Awareness can also shift with learning. As understanding deepens, awareness of certain aspects of experience increases. This reflects changes in neural networks that guide attention and interpretation. Another important aspect is that awareness does not require effort to exist. It arises naturally when the nervous system is functioning within certain parameters. Effort can shape awareness, but awareness itself is not something that must be produced. Understanding this can change how fluctuations are interpreted. Moments of reduced clarity or increased wandering are not failures. They are variations in regulation. As this section comes to a close, it becomes clear that awareness is not something separate from the nervous system's operations. It is one of their expressions. Awareness reflects integration, prediction, regulation, and continuity working together. As we move into this final section, the focus widens again, returning from moment-by-moment experience to the broader patterns that support long-term stability. By now, it may be clear that the nervous system is not only about reactions, sensations, or awareness. It is also about maintaining continuity over time, holding the body and mind in workable balance across changing conditions. Stability, in nervous system terms, does not mean remaining the same. It means remaining functional. It means preserving coordination, responsiveness, and coherence even as circumstances shift. This kind of stability is dynamic rather than fixed. One of the most important ways the nervous system supports long-term stability is through regulation of baseline activity. Baseline refers to the general level of activation around which moment-to-moment fluctuations occur. Heart rate, muscle tone, alertness, and emotional responsiveness all have baseline levels that vary between individuals and across life stages. The nervous system continually adjusts these baselines based on experience. If life has required frequent alertness and rapid response, baseline arousal may be higher. If life has been more predictable and contained, baseline arousal may be lower. These differences reflect adaptation rather than inherent traits. Baseline regulation is not consciously controlled. It emerges from repeated patterns of signaling across neural networks. Over time, these patterns become the default starting point for regulation. Importantly, baseline is not destiny. It can shift gradually in response to changing conditions. However, because baseline reflects long-term adaptation, shifts tend to be slow and cumulative rather than immediate. Another key contributor to long-term stability is redundancy. The nervous system rarely relies on a single pathway or mechanism to support essential functions. Multiple systems overlap, providing backup and flexibility. For example, breathing is regulated by several neural centers. If one pathway is disrupted, others can often maintain function. This redundancy protects against failure and supports resilience. Redundancy also applies to cognition and emotion. Multiple networks can support similar functions, allowing compensation when conditions change. Another principle underlying stability is modularity. The nervous system is organized into semi-independent modules that can operate somewhat autonomously while remaining coordinated with the whole. This organization allows localized adaptation without destabilizing the entire system. For instance, changes in sensory processing do not necessarily disrupt emotional regulation. Changes in motor control do not necessarily impair cognition. Modules adjust locally while remaining integrated globally. This modular organization supports robustness. Another factor supporting long-term nervous system stability is energy regulation. Neural activity is metabolically expensive. The nervous system carefully manages energy use, scaling activity up or down based on demand. During periods of high demand, energy is allocated toward relevant systems. During periods of low demand, energy use decreases. This flexibility supports sustainability. Over time, the nervous system learns which demands are worth sustained investment and which are transient. This learning influences how energy is allocated. Another important contributor to stability is rhythm. Biological rhythms, daily, seasonal, and activity-related, provide predictable structure. The nervous system uses rhythm to anticipate change and regulate accordingly. Rhythmic patterns reduce uncertainty. They allow the nervous system to prepare in advance rather than react constantly. Even irregular rhythms can become stabilizing if they are consistent enough to be predicted. Another stabilizing factor is feedback. Continuous feedback allows regulation to be corrected before deviations become large. This fine-tuning prevents drift. Feedback operates at multiple levels, from cellular signaling to whole-body responses. The nervous system uses feedback to adjust posture, emotion, attention, and internal physiology. Without feedback, regulation would be blind. With feedback, it is adaptive. Another important principle is tolerance. The nervous system does not aim to eliminate variability. It aims to tolerate it. Small fluctuations are expected and accepted. This tolerance prevents overcorrection. Overcorrection would destabilize the system by amplifying minor deviations. Healthy regulation involves allowing a range of variation without excessive response. Another stabilizing feature is prioritization. The nervous system continuously decides what matters most. This prioritization allows essential functions to be protected even under constraint. For example, during illness, energy may be diverted from non-essential activity toward immune response and maintenance. Cognitive sharpness may temporarily decrease to support recovery. These trade-offs reflect intelligent regulation rather than failure. Another long-term stabilizer is learning from outcome. The nervous system evaluates whether responses were effective and adjusts future responses accordingly. This learning happens gradually and often unconsciously. Over time, this outcome-based learning refines regulation. Another factor supporting stability is meaning. Experiences that are interpreted as meaningful engage neural networks that support motivation and coherence. Meaning buffers stress and supports regulation. Meaning does not require intensity. Familiar, valued routines can be meaningful. Another stabilizing influence is social connection. Social interaction influences nervous system regulation at multiple levels. Supportive interaction can stabilize baseline arousal and emotional responsiveness. This influence operates through neural, hormonal, and behavioral pathways. Another important point is that stability is context-dependent. The same nervous system may be stable in one environment and less so in another. Stability reflects the match between regulatory patterns and environmental demands. When demands change, stability may temporarily decrease while adaptation occurs. This temporary instability is not failure. It is part of recalibration. Another key concept is that long-term nervous system health is not defined by absence of fluctuation. It is defined by recovery. The ability to return toward baseline after challenge matters more than maintaining constant equilibrium. Recovery reflects regulatory capacity. This capacity is supported by redundancy, feedback, rhythm, and learning. Another important observation is that stability often becomes more visible during challenge. When conditions are easy, regulation is unnoticed. When conditions change, regulatory processes come into focus. This visibility does not mean the system is struggling. It means it is working. Another principle is that nervous system stability is relational. It depends on interaction between internal processes and external conditions. Neither alone determines outcomes. This relational nature means that changes in environment can support or strain regulation. As we move further into this section, we will continue exploring how these stabilizing principles apply across everyday life, how they support continuity of function, and how understanding them can shift how fluctuations are interpreted. For now, allow this broader picture to settle. Stability, in nervous system terms, is not about stillness. It is about coordinated movement through time, supported by countless quiet adjustments working together beneath awareness. As this exploration continues, everyday life comes into clearer focus. The nervous system does not operate only during moments of intensity or change. It is shaped, supported, and regulated by ordinary patterns, the repeated rhythms and small choices that make up daily experience. These patterns interact quietly with the stabilizing mechanisms already described. One of the most influential everyday factors is regularity. Regularity does not mean rigidity. It means having enough consistency that the nervous system can anticipate what comes next. Anticipation reduces uncertainty, and reduced uncertainty lowers regulatory load. When certain aspects of the day follow familiar patterns, waking, eating, moving, resting, the nervous system spends less energy monitoring for surprise. This conserved energy can be used for flexibility elsewhere. Importantly, regularity does not require strict schedules. Approximate timing and familiar sequences are often sufficient. The nervous system responds to patterns, not precision. Another everyday influence is environmental familiarity. Familiar spaces provide predictable sensory input. The nervous system already knows how light, sound, and spatial layout behave in these environments. This predictability supports calm regulation. Unfamiliar environments require increased monitoring. The nervous system must update predictions and remain alert to unexpected input. Over time, as environments become familiar, regulatory demands decrease. This is why transitions, such as moving to a new home or adjusting to new routines, can temporarily increase regulatory load. The system must learn new patterns. Another important factor is sensory load. Everyday environments vary in the amount and type of sensory input they provide. Noise, visual complexity, and movement all influence nervous system activity. Moderate sensory input supports engagement and orientation. Excessive or chaotic input can increase regulatory demand. Insufficient input can reduce stimulation and engagement. The nervous system continually adjusts sensitivity to manage this load. Over time, repeated exposure shapes baseline sensitivity. Another everyday influence is posture and movement. How the body is positioned influences sensory input and neural signaling. Upright posture, gentle movement, and changes in position provide feedback that supports regulation. Prolonged immobility or constrained posture can alter sensory feedback and increase regulatory demand. The nervous system responds by adjusting muscle tone and attention. Movement does not need to be strenuous to influence regulation. Small, regular movements provide valuable input. Another key everyday factor is social rhythm. Interaction patterns, conversation, shared activity, quiet presence shape neural regulation. Predictable social contact supports stability. Unpredictable or conflicting interaction can increase load. The nervous system responds not only to what is said, but to tone, timing, and consistency. These cues influence emotional and physiological regulation. Even brief, low-intensity social contact can have stabilizing effects when it is predictable and supportive. Another everyday influence is cognitive pacing. The nervous system responds to how tasks are sequenced. Alternating periods of focus and rest supports regulation. Prolonged high demand without recovery increases load. Recovery does not need to be passive. Shifting to lower demand activities allows regulatory systems to recalibrate. The nervous system benefits from variation within limits. Repeated patterns, punctuated by gentle novelty, support engagement without overload. Another important factor is attention distribution. Where attention is repeatedly directed, shapes neural networks. Sustained attention toward certain types of information strengthens related pathways. This does not mean attention must be controlled forcefully. It means that repeated patterns matter. For example, repeatedly attending to neutral or meaningful information supports different regulatory patterns than repeatedly attending to threat or uncertainty. Another everyday influence is decision density. The number of decisions required in a day influences regulatory load. Many small decisions can accumulate demand, even if each decision is minor. Reducing unnecessary decision-making through routines or defaults conserves regulatory resources. This conservation supports flexibility when decisions truly matter. Another stabilizing factor is predictability of outcome. When actions reliably lead to expected outcomes, the nervous system learns that the environment is controllable. This supports stable regulation. Unpredictable outcomes increase monitoring and reduce confidence in prediction. Over time, this can increase baseline arousal. This does not mean outcomes must always be positive. They must be consistent enough to be learned. Another everyday influence is emotional context. Emotional tone of daily experience influences baseline regulation. Repeated exposure to calm or neutral emotional environments supports stability. Repeated exposure to conflict or uncertainty increases demand. The nervous system adapts to emotional context just as it adapts to sensory context. Another factor is bodily comfort. Physical discomfort, temperature extremes, pain, hunger creates ongoing signals that require regulation. Managing basic comfort reduces baseline load. This reflects the integrated nature of nervous system function. Regulation depends on bodily state. Another everyday influence is meaning attribution. How experiences are interpreted influences neural response. When experiences are framed as manageable or meaningful, regulatory systems respond differently than when experiences are framed as overwhelming. This framing does not require conscious effort. It emerges from repeated narrative patterns. Another stabilizing factor is expectation alignment. When expectations match reality, prediction errors are small and easily resolved. When expectations are consistently violated, regulatory demand increases. Adjusting expectations to better match reality reduces load. Another everyday influence is recovery timing. Allowing recovery before demands accumulate supports regulation. Waiting until fatigue is extreme makes recovery slower. This reflects the nervous system's preference for gradual adjustment rather than crisis response. Another important point is that everyday patterns do not need to be optimized perfectly. The nervous system is tolerant of imperfection. It adapts to approximate regularity and moderate variability. Seeking perfection increases regulatory load. Another stabilizing influence is familiarity of tasks. Familiar tasks require less monitoring and allow automatic processing. This frees resources for other demands. Learning new tasks increases load initially, but can support long-term adaptability once patterns are established. Another everyday factor is the pace of change. Gradual change allows the nervous system to adapt. Abrupt change increases load temporarily. This principle applies to routines, environments, and roles. Another important observation is that everyday life provides continual feedback. The nervous system learns from outcomes and adjusts regulation accordingly. This learning happens whether or not it is noticed. Over time, these small adjustments accumulate, shaping baseline regulation. As we continue toward the end of this exploration, it becomes clear that long-term nervous system stability is built from ordinary moments rather than extraordinary ones. The system responds to what is repeated. Understanding this shifts perspective. Stability is not something to achieve once and maintain forever. It is something that is continuously supported through patterns of interaction with the world. As this exploration continues, everyday life comes into clearer focus. The nervous system does not operate only during moments of intensity or change. It is shaped, supported, and regulated by ordinary patterns, the repeated rhythms and small choices that make up daily experience. These patterns interact quietly with the stabilizing mechanisms already described. One of the most influential everyday factors is regularity. Regularity does not mean rigidity. It means having enough consistency that the nervous system can anticipate what comes next. Anticipation reduces uncertainty, and reduced uncertainty lowers regulatory load. When certain aspects of the day follow familiar patterns, waking, eating, moving, resting, the nervous system spends less energy monitoring for surprise. This conserved energy can be used for flexibility elsewhere. Importantly, regularity does not require strict schedules. Approximate timing and familiar sequences are often sufficient. The nervous system responds to patterns, not precision. Another everyday influence is environmental familiarity. Familiar spaces provide predictable sensory input. The nervous system already knows how light, sound, and spatial layout behave in these environments. This predictability supports calm regulation. Unfamiliar environments require increased monitoring. The nervous system must update predictions and remain alert to unexpected input. Over time, as environments become familiar, regulatory demands decrease. This is why transitions, such as moving to a new home or adjusting to new routines, can temporarily increase regulatory load. The system must learn new patterns. Another important factor is sensory load. Everyday environments vary in the amount and type of sensory input they provide. Noise, visual complexity, and movement all influence nervous system activity. Moderate sensory input supports engagement and orientation. Excessive or chaotic input can increase regulatory demand. Insufficient input can reduce stimulation and engagement. The nervous system continually adjusts sensitivity to manage this load. Over time, repeated exposure shapes baseline sensitivity. Another everyday influence is posture and movement. How the body is positioned influences sensory input and neural signaling. Upright posture, gentle movement, and changes in position provide feedback that supports regulation. Prolonged immobility or constrained posture can alter sensory feedback and increase regulatory demand. The nervous system responds by adjusting muscle tone and attention. Movement does not need to be strenuous to influence regulation. Small, regular movements provide valuable input. Another key everyday factor is social rhythm. Interaction patterns, conversation, shared activity, quiet presence shape neural regulation. Predictable social contact supports stability. Unpredictable or conflicting interaction can increase load. The nervous system responds not only to what is said, but to tone, timing, and consistency. These cues influence emotional and physiological regulation. Even brief, low-intensity social contact can have stabilizing effects when it is predictable and supportive. Another everyday influence is cognitive pacing. The nervous system responds to how tasks are sequenced. Alternating periods of focus and rest supports regulation. Prolonged high demand without recovery increases load. Recovery does not need to be passive. Shifting to lower demand activities allows regulatory systems to recalibrate. The nervous system benefits from variation within limits. Repeated patterns, punctuated by gentle novelty, support engagement without overload. Another important factor is attention distribution. Where attention is repeatedly directed, shapes neural networks. Sustained attention towards certain types of information strengthens related pathways. This does not mean attention must be controlled forcefully. It means that repeated patterns matter. For example, repeatedly attending to neutral or meaningful information supports different regulatory patterns than repeatedly attending to threat or uncertainty. Another everyday influence is decision density. The number of decisions required in a day influences regulatory load. Many small decisions can accumulate demand, even if each decision is minor. Reducing unnecessary decision-making through routines or defaults conserves regulatory resources. This conservation supports flexibility when decisions truly matter. Another stabilizing factor is predictability of outcome. When actions reliably lead to expected outcomes, the nervous system learns that the environment is controllable. This supports stable regulation. Unpredictable outcomes increase monitoring and reduce confidence in prediction. Over time, this can increase baseline arousal. This does not mean outcomes must always be positive. They must be consistent enough to be learned. Another everyday influence is emotional context. Emotional tone of daily experience influences baseline regulation. Repeated exposure to calm or neutral emotional environments supports stability. Repeated exposure to conflict or uncertainty increases demand. The nervous system adapts to emotional context just as it adapts to sensory context. Another factor is bodily comfort. Physical discomfort, temperature extremes, pain, hunger creates ongoing signals that require regulation. Managing basic comfort reduces baseline load. This reflects the integrated nature of nervous system function. Regulation depends on bodily state. Another everyday influence is meaning attribution. How experiences are interpreted influences neural response. When experiences are framed as manageable or meaningful, regulatory systems respond differently than when experiences are framed as overwhelming. This framing does not require conscious effort. It emerges from repeated narrative patterns. Another stabilizing factor is expectation alignment. When expectations match reality, prediction errors are small and easily resolved. When expectations are consistently violated, regulatory demand increases. Adjusting expectations to better match reality reduces load. Another everyday influence is recovery timing. Allowing recovery before demands accumulate supports regulation. Waiting until fatigue is extreme makes recovery slower. This reflects the nervous system's preference for gradual adjustment rather than crisis response. Another important point is that everyday patterns do not need to be optimized perfectly. The nervous system is tolerant of imperfection. It adapts to approximate regularity and moderate variability. Seeking perfection increases regulatory load. Another stabilizing influence is familiarity of tasks. Familiar tasks require less monitoring and allow automatic processing. This frees resources for other demands. Learning new tasks increases load initially, but can support long-term adaptability once patterns are established. Another everyday factor is the pace of change. Gradual change allows the nervous system to adapt. Abrupt change increases load temporarily. This principle applies to routines, environments, and roles. Another important observation is that everyday life provides continual feedback. The nervous system learns from outcomes and adjusts regulation accordingly. This learning happens whether or not it is noticed. Over time, these small adjustments accumulate, shaping baseline regulation. As we continue toward the end of this exploration, it becomes clear that long-term nervous system stability is built from ordinary moments rather than extraordinary ones. The system responds to what is repeated. Understanding this shifts perspective. Stability is not something to achieve once and maintain forever. It is something that is continuously supported through patterns of interaction with the world. In the next and final part, we'll complete Section 4 by bringing these ideas together, connecting moment-to-moment processes, long-term adaptation, and everyday patterns into a unified understanding of nervous system function. For now, allow this view of everyday influence to rest where it is. Like the nervous system itself, it works quietly in the background, shaping regulation through repetition rather than force. Continue. Section 4 CI. As we move into this final stretch, the many threads we've explored begin to naturally converge. The nervous system does not operate in compartments. Moment-to-moment regulation, long-term adaptation, and everyday patterns are not separate processes. They are different expressions of the same underlying principles, unfolding at different timescales. At its core, the nervous system is always doing the same fundamental work. It is sensing, predicting, responding, and updating. Whether this happens over milliseconds, hours, or decades, the logic remains consistent. What changes is the scope. Moment by moment, the nervous system adjusts attention, perception, and readiness. Across days and weeks, it adjusts baselines and expectations. Across years, it reorganizes strategies and priorities. These layers sit on top of one another, influencing and reinforcing each other. One of the most important unifying principles is efficiency. The nervous system continually seeks to reduce unnecessary effort. It does this by learning what can be predicted, what can be automated, and what deserves focused attention. Over time, this efficiency supports stability. Efficiency does not mean minimizing activity. It means using activity wisely. The nervous system invests resources where they matter and withdraws them where they do not. Another unifying principle is adaptability. Adaptation does not require dramatic change. It occurs through countless small adjustments. Each experience slightly shifts prediction, sensitivity, or response. Most of these shifts are invisible. Adaptation is therefore not something that happens only during crisis. It is constant. This constant adaptation allows the nervous system to remain aligned with current conditions rather than locked into outdated patterns. Another key principle is coherence across levels. Cellular processes, neural circuits, whole body regulation, and subjective experience all influence one another. No level operates independently. For example, changes in cellular signaling influence network dynamics. Network dynamics influence attention and emotion. Attention and emotion influence behavior and environment. Environment feeds back into cellular signaling. This circularity means that change at one level can influence others, even if the pathway is indirect. Another important principle is tolerance. The nervous system does not require perfect conditions to function well. It tolerates noise, variability, and imperfection. In fact, some variability is essential for learning and flexibility. Attempting to eliminate all variability would reduce adaptability. Tolerance allows the nervous system to absorb fluctuations without destabilizing. Another unifying idea is timing. The nervous system is exquisitely sensitive to timing. When things happen, matters as much as what happens. This applies to sensory input, motor coordination, recovery, and learning. Proper timing allows integration. Poor timing increases regulatory demand. This sensitivity to timing explains why spacing, pacing, and rhythm are so influential. Another important principle is proportional response. The nervous system continually scales responses to match perceived demand. When demand is low, responses are minimal. When demand increases, responses scale up. Problems arise when scaling becomes mismatched, either because demands are misinterpreted or because regulatory thresholds have shifted. Understanding proportionality helps reframe many experiences. Strong responses often reflect perceived demand rather than actual threat. Another unifying concept is history dependence. The nervous system always carries its history forward. Past adaptations influence present regulation. This history dependence explains individual differences. Two people may respond differently to the same situation because their nervous systems have learned different patterns. This does not mean one response is correct and the other incorrect. It means adaptation reflects experience. Another important idea is that nervous system function is contextual. The same internal state may feel very different in different environments. Context shapes interpretation. This contextual sensitivity allows flexible behavior, but also means that regulation depends on fit between internal patterns and external conditions. Another unifying principle is gradualism. The nervous system prefers gradual change. Sudden shifts require rapid recalibration and increased load. Gradual shifts allow prediction to update smoothly. This principle applies to learning, habit change, and adaptation across the lifespan. Gradual change supports sustainability. Another key concept is self-maintenance. The nervous system invests in preserving its own function. It allocates resources toward repair, recalibration, and protection. This self-maintenance is not conscious. It emerges from regulatory mechanisms evolved to support survival and continuity. Another important idea is that regulation is relational rather than isolated. The nervous system does not regulate itself in a vacuum. It regulates in relation to body, environment, and social context. This relational nature means that support can come from outside the individual, as well as from internal processes. Another unifying principle is that awareness is an outcome, not a controller. Awareness reflects what the nervous system is doing. It does not direct most regulation. Understanding this can reduce the urge to control processes that are better left to automatic regulation. Another important idea is that nervous system health is not about constant comfort. It is about capacity. Capacity to respond, adapt, recover, and continue. Discomfort does not mean failure. It often signals adjustment. Another principle is that the nervous system is conservative. It prefers familiar solutions. Novel responses require more energy. This conservatism supports efficiency, but can slow change. Repeated exposure to new patterns under manageable conditions allows conservative systems to update. Another unifying idea is that regulation is layered. Fast processes adjust quickly. Slow processes adjust gradually. These layers interact. Fast adjustments handle immediate demands. Slow adjustments shape baseline. Understanding this layering helps explain why immediate changes do not always produce lasting effects. Another important principle is that nervous system function is probabilistic. It deals in likelihoods, not certainties. Responses are best guesses based on available information. This probabilistic nature allows flexibility, but also means variability. Variability is not error, it is exploration. Another unifying concept is integration of meaning. Meaning influences prediction and prioritization. Experiences perceived as meaningful engage regulation differently than those perceived as arbitrary. Meaning supports coherence. Another important idea is that nervous system regulation is invisible when it works well. It comes into awareness mainly when demands increase or patterns change. This invisibility can make regulation seem fragile when it is actually robust. As we approach the final part, the picture becomes clear. The nervous system is not a fragile machine that must be kept in perfect balance. It is a resilient, adaptive system that maintains function through continual adjustment. Understanding this shifts perspective. Fluctuations are not signs of failure. They are signs of life. In the final part, we'll bring everything together by reflecting on what this understanding means for how we relate to our own experience and to change itself without instruction, without effort, simply as a way of seeing. For now, allow these ideas to settle naturally. Like the nervous system itself, understanding does not need to be forced. It organizes quietly, over time, through gentle repetition. As we arrive at this final part, there's no need to summarize or draw conclusions in a formal way. The nervous system itself does not work by wrapping things up neatly. It works by allowing understanding to settle, integrate, and quietly reshape how experience is interpreted over time. What may stand out now is how consistent the nervous system's principles are. Whether we look at milliseconds or decades, the same patterns repeat. Sensing, prediction, response, adjustment, again and again, not as a struggle, but as a rhythm. The nervous system is not asking to be managed moment by moment. Most of what it does is automatic, reliable, and deeply practiced. Long before conscious thought appears, regulation is already underway. This is not something to improve upon. It is something that has been refined across a lifetime. One of the most important shifts that can occur through understanding is a change in relationship. When the nervous system is seen as adaptive rather than fragile, many experiences take on a different meaning. Fluctuation becomes information rather than threat. Change becomes adjustment rather than failure. Awareness of this does not require effort. It does not require monitoring sensations or correcting responses. It simply alters interpretation, and interpretation influences regulation. Another quiet realization is that the nervous system is not oriented toward comfort alone. It is oriented toward continuity. Comfort may come and go. Stability is maintained through flexibility, not through eliminating challenge. This perspective helps place everyday experiences into context. Moments of restlessness, fatigue, alertness, or dullness are not signals that something is wrong. They are signals that the system is responding to conditions, conserving energy, reallocating resources, or updating expectations. The nervous system does not expect consistency from the world. It expects change. Its design reflects this expectation. Another important understanding is that regulation does not belong to the individual alone. It is distributed. Environment, routine, social contact, and physical context all participate. Support does not weaken regulation. It strengthens it. This is why small, ordinary consistencies can have such a stabilizing effect. Familiar spaces, predictable rhythms, gentle engagement. These are not minor details. They are part of how regulation is supported. The nervous system also does not require constant attention to function well. Excessive monitoring can increase load rather than reduce it. Trusting automatic processes allows regulation to proceed without interference. This trust is not blind. It is based on understanding how resilient and adaptive the system truly is. Another important point is that nervous system health is not defined by the absence of difficulty. It is defined by the ability to move through difficulty and return toward balance. Recovery matters more than avoidance. Recovery does not mean immediate resolution. It means gradual recalibration. The nervous system is patient by design. It works on timescales that do not always align with conscious expectation. This patience supports sustainability. As life continues to change, the nervous system continues to adapt. There is no final state where adjustment ends. This ongoing adaptation is not a burden. It is what allows continuity of identity and function across time. Understanding this can bring a quiet sense of steadiness, not because conditions will always be easy, but because regulation does not depend on ease alone. It depends on adaptability. The nervous system has already adapted to countless changes. It has learned from success and from difficulty. It carries that learning forward into each new moment. There is nothing additional it needs to be taught right now. If you've been listening passively, that is enough. If your attention drifted at times, that is expected. The nervous system absorbs information in layers, not all at once. Even now, integration continues quietly. As this narration comes to a close, there's nothing you need to hold on to. The understanding that matters most does not require recall. It shows up later, subtly, in how experiences are interpreted and responded to. If this exploration of the nervous system felt helpful or grounding in any way, you're gently invited to like the video and subscribe to Quiet Vitality. New long-form, calm, health-focused explanations are added regularly, designed to be listened to at your own pace. Thank you for spending this time here, wherever you are, and whatever time it happens to be for you.